The agenda for today's talk is to derive the non-central chi-square distribution, and then we're going to illustrate this distribution within R. We're going to investigate the non-central chi-squared with 1 degree of freedom. We're going to look at what happens when you increase the degrees of freedom and when you increase the non-centrality parameter. So to start, we're going to define some variables. We're going to let xi's be normal mu I, and this is from 1 to k. We're going to let y1 be normal lambda to the 1/2 power, and where lambda is the sum of the mu I squareds defined with the x's. And then we're going to let yi from 2 to k be normal 0, 1. And in another video, well, here we're interested in the sum of these xi squareds. In another video that I uploaded to YouTube, we showed that modeling this is going to be the same as modeling the yi squareds, where y1 squared will let be the variable u, and the sum of the from 2 to k of the yi's be v. And we also showed that these two variables are independent. The first one is a non-central chi-squared with 1 degree of freedom, and v is distributed as a chi-squared with k-1 degrees of freedom. So the density that we derived of this variable u is this. This is the non-central chi-squared with 1 degree of freedom. And remember this because we're going to put this exactly into R and then compare it with the density function that's used in R and show that they're 100% equivalent. The density function for v with k-1 degrees of freedom is this, and their joint densities are the product of two because they're independent. So now we're going to define some variables here. We have u and v, which is in R2 space, so we have to map to R2 space. But this is the variable of interest. It's the sum of the yi squareds, which is equivalent to the sum of the xi squareds. But since we're going from R2, we have to map to R2, so let's create a variable t, which is the chi-square distribution. The Jacobian of this transformation, you can show that it's 1. And here would be the joint density function for w and t, where we plug in u of this for that non-central chi-squared with 1 degree of freedom, and f of v, where we plug in t for v, and the Jacobian is 1. So here we go. Now this first part was the non-central chi-squared with 1 degree of freedom, and we plugged in y minus t in for the variable in every place. And then we plugged in t for v in the chi-square distribution, and we get this. Now this can be simplified, but I'm going to go straight to integrating out t, which will leave w. Now one note here, that the chi-square goes from 0 to infinity, but in our setup, v can't be greater than w. So we integrate t from 0 to w. And that's this. So we take the joint density and integrate out t from 0 to w. And we have this. We pull out all the constants, which is anything without a t, and this is what is left over. Now we're finished, because this can't be simplified farther, and it has to be solved by numerical methods. So w, which is the sum of the xi squareds, is a non-central chi-square distribution with k-1 degrees of freedom, non-centrality parameter lambda, which is the sum of the mu I squareds. Now one note is that, and what is often done to give this a different look, is they take this piece of it and replace it with a hyperbolic cosine function, which is the average of these two exponentials, and that's what we have here. They take one of these twos and put it here, and then they put it with the hyperbolic cosine function. Well, then you can take the Taylor expansion of that variable, and then they will make a substitution. Instead of w minus t, they'll pull out a square root of w, leaving 1 minus t over w to the 1/2 power. And they do this because then it kind of tricks this into looking like a beta function. And so then we know how to integrate beta functions, and this then, after all this substitution and manipulation, it can be shown that this distribution is a sum of chi-square distribution with Poisson weights. But we're not going to do that. We're just going to leave it here and then be done with it. And now on to R. We're in R right now, and we're going to look at the non-central chi-square distribution. First, we're going to look at the non-central chi-square distribution with 1 degree of freedom, and this was the formula that we derived in the video earlier, and we're going to call that chi1. And then we're going to compare that with the built-in distribution or density function in R. So we're going to look at the value of 5, degrees of freedom 1, non-centrality parameter 3. And if you look down here, it's the same exact value. And we can change the non-centrality parameter to 7, and we produce the same thing. We can change the y value from 5 to 22 and then recalculate it, and it's the same value. And just wanted to show you that whatever R is using is equivalent to that formula. Well, they should be the same. So now let's look at what degrees of freedom does to a chi-squared. So we'll start out with 1 degree of freedom and then increment it in steps of 5, and let's see what it does. So this is the chi-square with 1 degree of freedom, and then this is 5, and this is 10, 15, 20, and 25. You can see that the distribution keeps shifting to the right, and that is important. Now, degrees of freedom is often associated with sample size, and so this becomes important when you're looking at power and you have a cutoff region, and increasing sample size shifts the distribution, which increases power. But you can kind of see the distributional shift. Now, if we remember this one here, degrees of freedom 25, I'm going to replot that on a different scale, and then look what happens when we change the non-centrality parameter. So this was that the central chi-square distribution with 25 degrees of freedom. And actually all of these are with 25 degrees of freedom, but we're incrementing the non-centrality parameter by steps of 5. So this is NCP of 5, 10, 15, 20, and 25. And then we can also see that the distribution shifts to the right when you increase the non-centrality parameter. So that's 2 ways that you can shift the chi-square distribution to the right, is increasing the degrees of freedom and increasing this non-centrality parameter, which becomes very important when you're calculating power and sample size. And that's it. Hope you enjoyed it.